All right, check, mic check. All right. All right, so we're picking up where we left off from before. And when we left, we had created our DEM and we had created our difference raster. That is the difference between our water and our topography. Now, I drew a little picture here to show what's going on, right? So here I have elevation, right? And that's the topography of the land, the river channel. Right here in the center, okay, is the water level from where we measured it with our profiles, right? This line here represents the water level there. If we subtract, okay, the land from this water level, we kind of get an inverse here of the topography, right? So now what we're about to walk through is if we have a 20% or 20-foot increase in the level of the water, okay, how much area does that flood out and how much water does it take to do that? Okay, we're going to answer both of those questions right now. So here's our difference, right? And let's look at that in a couple of different ways real quick. I'm going to create 3 classes in my classification, all right? And all values that are at or about 0, say anything from 0 to 1, that is going to be what I'm calling my water level, okay? And then I'm interested in a 20-foot increase in that, okay? So I'm answering both of those questions here. So what do I have? So this is the whole area that I created the little floodplain model of. This black area in here is the actual area covered by the water at the 0 water level, okay? That the black pixels, that's how much area is covered by the water at that level. If the water level increases by 20 feet, okay, this gray shows the additional area that's required to contain the water at that level, all right? Okay, so, all right, so to answer the first question, how much area does that represent? Well, we just create a little mask for that using the raster calculator tool. So you pull up raster calculator and you say, give me my difference pixel, a difference raster where the pixel values are less than or equal to 20. And I'm going to call this difference mask 20. Take it just a second to run. What it returns is a raster with only 2 values. Those pixels that are included in that condition and the pixels that are not. Okay, so now I have a mask. I simply count those pixels multiplied by the resolution, and there I have the area. So that's question 1. Now question 2 asks, how much water does it take to have the water fill in that much area? So let's go back to my little conceptual model here. At 20 feet elevation increase, right? All I need to do is subtract the difference value that was the inverse of the topography, right? And then I'll have the voxels that it would take to fill that area. Right? 1 voxel, 1 unit multiplied by the area. Its height is 1, and then we know the cubic volume that it takes. So let's work that out. How do I do that? Oh, first, go to raster calculator again. 20 feet minus that difference raster. Okay. So this is the difference minus 20. Now I need to exclude the areas where my mask said it was 0 times my mask, right? And this is going to be the voxels needed at 20 feet. So as expected, still no water. Oh, gotta change this so we can look at our voxels. Those are all at 0. And here we now have the depth of the water in voxels. So what we need to know then is how many voxels, and then we multiply that by the resolution, and then we have the volume of water. And to calculate that, I think it's easiest if we use zonal statistics as table, just because that's always the tool that helps us out. So the feature zone is going to be our mask, and the input value is going to be vox20, and this is going to be the zonal sum, and we need the sum. So if I open that up, that's how many voxels. That's how many total voxels. So we'll take note of that. And that's in square feet. So if I want to calculate, let's say the volume, right? The volume in, we'll say feet cube. It's simply going to be the sum times the resolution, which in this case, I believe is 5. You know, we better check that. It's really easy to check. We'll just go into the source here. Oh, no, it's 10. 10 feet. See, I almost made a mistake. Sum times 10 times 10. Now that's in feet. Cubic feet. Now you could do some math to turn it into something else, but cubic feet works for me, okay? So, all right, so that's our water depth, and we know the cubic feet. Okay, we know the cubic feet, right? So what does that mean here? So if that area in there, let's see, how many cubic feet was that? How many cubic feet? Let's copy that, paste it right there. All right, it's that many cubic feet. And what else do we know? What is the area occupied there at the top? Excuse me, the total area. The total area. Right, so that's how much water is needed to fill that channel. So, okay, to fill that channel. Now, how much, how can that be converted into, say, rainfall? You know, in rainfall, you simply take the area of your whole watershed. So here we're just saying that this is a self-enclosed basin. It's not, but if it were, it's simply the area multiplied by however much precipitation there was. So if this were, 100 square feet, say, and you got, 1 inch of rain, you would have, however that math works out. But however much rain times the area, that's what's got to be figured out. Yep. And then that gives you a total, and then you can know then, is that total, does that push you to this level or not? Okay. So I know that was a lot of steps here, but that's how we figure out at a 20-foot change in water level, here's the area that's impacted, and then we just walk through the math of how to calculate how much water there is. Okay. So we'll pick up here, and if this needs to be kind of modified a little bit to be more clear, we'll do that too.